I'd like to welcome you to the talk about the newest discoveries in the solar system. And so the solar system is just, of course, a very tiny part of the entire universe, and that's why it's hard to teach astronomy in just one quarter or something. We're talking about everything in the whole universe here. So you may recognize me if you've been to the planetarium, but unfortunately COVID, at least for now, has ended that part of my career. So anyway, I also have taught astronomy for a long time at Spokane Falls Community College, and I'm going to be teaching astronomy again here at Chesterton Academy coming up this fall, so kind of looking forward to that. So I love talking to public groups, though, about astronomy. It's really great to be able to share the wonder and mysteries that we have of the universe and share them with people here. And we're talking about the new discoveries in the solar system. Many of these, I'm hoping practically all of them will be brand new to you, but I find that they're all interesting in their own way. So hopefully I'll also get some feedback from you. If something is new or I'm not explaining it well enough, feel free to go ahead and ask away, because I love questions and I want to hopefully get you to understand what I'm talking about here and not just let it slide by without asking a question. So please do that. So before I move from our title slide here, you might recognize the planet there in the middle. That's our Earth, of course. And the one just to the left of that is, anyone guess what this one is? Venus. That's right. So Venus is, if you notice, this is to scale, and so Venus is very close to the Earth in size. We'll talk a little more about that as we get moving here. The patterns of clouds that you see there are actually seen in the ultraviolet region of the spectrum. It turns out invisible light is practically featureless, with almost no noticeable cloud bands or anything. And underneath the clouds, it's very different than the Earth, much more different than people expected. And to the right there, we have two other, I guess I'll just call them planets. One of them is Mars, of course, the red planet, and you can see the reddish color of its soil on its surface. And below that, we have the Earth's moon. And if you notice, the Earth's moon is getting close to the size of the other planets. It's very close, actually, to the size of Mercury, but it's Earth and the moon are very frequently referred to as a double planet. And so the Earth and its moon, for planets anyway, that's the largest ratio of moon to planet. The moon is actually quite significantly large for a planet in the solar system. So let's move on out now. And I just threw this in there so that if any of you wonder what I do, I built this telescope. It's not probably as visible as you can see there, but I want to come out here so I can just point it out. So this is the structure of my telescope right there. And so it's about 15 feet tall when we get it out to look at it. And it's got a backdrop of the Milky Way there and the stars. So anyway, that's kind of what I love to do as an amateur astronomer. So let's start at the first planet in the solar system, and that is Mercury. And many times people mistake the moon and Mercury because they look very similar, especially at first glance. Now when you get kind of used to it, you can kind of identify Mercury apart from the moon because they are somewhat different. You might notice that the crater sizes on Mercury are somewhat smaller than they are on the moon. And the crater bottoms are typically less dished out than they are on the moon. And so it is a little different. There's less of the large dark spots on Mercury as there are on the moon. The moon, especially the side that faces the Earth all the time, it has very large basins where ancient lava flows have filled those in, and you kind of see the man in the moon and things like that. So this is Mercury. And Mercury is the smallest planet in the solar system. That's no longer Pluto. It is not a planet. It is now classified as a dwarf planet. And there's actually very good reasons why we've done that. I don't want to go into the long lecture about why that's so, but let's just say in the 1800s, when we were first discovering, primarily just with the naked eye, they were discovering other bodies in the solar system. But we figured out as they orbited the sun that they were pretty close to the Earth, and they lie in what we call the asteroid belt. So that's between Mars and Jupiter, and they were just barely visible to the unaided eye. And so that would indicate that they've got to be very small compared to the other planets. But nonetheless, astronomers were trying to keep track of these, and they started calling them planets. So in the mid-1800s, we had something like 13 planets. Many people don't know that or remember that. And at a certain point, the astronomers just got together and decided, hey, these aren't planets like the other planets. They're way too small. And so that's when they became known as the minor planets. And we've done the same thing with Pluto, because we discovered Pluto way back in 1930, but now we know of several other bodies way out there beyond Neptune, but some of them turned out to be bigger than Pluto. And astronomers didn't want these to be classified as planets either, but if we didn't classify them as planets, Pluto would have to be removed of its name as a planet. So Pluto and several other bodies are now known as minor planets. And so Mercury then becomes the smallest of the 8 planets in the solar system. So hopefully that makes some sense. Any questions about that? Okay, so we've been through this exercise before. It's not like a brand new thing where it was just voted out because it's ugly or something. So anyway, so this was imaged by the Messenger spacecraft. That was the most recent one that's been to Mercury. This is actually a little ways back in time now, about 10 years ago. So that's not the new discovery I'm going to talk about here, but nonetheless I wanted to kind of get an introduction here to Mercury. And this is the same image, but it's very much contrast enhanced. And so the very slight subtle differences in color have been really turned up. And that's how we get this very colorful image, but your unaided eye, of course, can't really see these very subtle gradations in color. And so again, it's the innermost planet. So it's very warm, closer to the sun, but it's not the planet with the highest surface temperature. We'll get to that. But Mercury's surface temperature is around 800 degrees Fahrenheit. And it's got a very high density, but not the highest. The highest density planet is the Earth. So the Earth has got the highest density, but Mercury's right behind it with a very high density as well. That's mainly because being that close to the sun, most of the volatiles or low melting point materials were driven out of the inner solar system during its formation. And so there's very little water in this area of the solar system, and hence only the more refractory materials are left to make Mercury. So that's why it's got a higher density than many of the other planets, although not higher than the Earth. And we basically say it has no atmosphere. Now it might have a little bit of atmosphere. That would be primarily argon gas, maybe some helium, but helium isn't going to stay long term, but it does collect some helium from the solar wind. So the solar wind can kind of stick around because of the gravitational pull of Mercury, but it doesn't hang on to it long term. But it does have a tenuous atmosphere of a little bit of argon and helium. So, the first discovery is that Mercury, we've discovered, has geomagnetic storms. Now this is something we did not expect with Mercury. Now we did know for a while that it has a magnetic field, and we shouldn't be that surprised. The magnetic field is primarily created by the iron in the core of Mercury. And so a very long time ago in the history of the solar system, that magnetic field would be created by the churning of the liquid iron in its core, but over about the 4.5 billion year history of Mercury, most of that has now frozen out. But there's a residual amount of magnetic field from when it did have a magnetic field. And so that will persist for who knows how long. It won't go away. And so these geomagnetic storms are very interesting in that there's got to be some interaction between the solar magnetic field and then Mercury's magnetic field. And that interaction is what allows for these storms or perturbations of the magnetic field to occur and be what we call magnetic storms. So because of its Earth-like magnetic field, the interactions between it and the sun, as I already suggested, can cause it to have storms or disturbances in that. And that has implications then for other planets, especially when we look at other planets outside our solar system. And so those planets are known as exoplanets. So they're beyond our solar system. And we now know of about 6,000 other planets outside of our solar system. And so they're very difficult to examine them directly when they're so far away and they're so close to their host star that it's very difficult to directly image them or know a whole lot about them. But now that we know that these geomagnetic storms can occur even on small, relatively dead bodies like Mercury, that brings more interesting things to study about these exoplanets. And another discovery is that Messenger, this spacecraft, the last one at least that was functioning around Mercury, also confirmed that there is water ice in some of the craters near its poles. So it does turn on its axis, not very fast, but near its poles, and this is the North Pole, I believe, and this is the South Pole, but these craters near enough to the poles can actually be deep enough where sunlight very rarely can reach the floor of the craters and allows ice to build up in those areas. So this is probably ice that came via comets, and that cometary ice, when it was buried in these crater floors where the sun very rarely ever shines on those crater floors, it can allow that ice then to stay there, especially if it gets buried with a small layer of dust over the ice. It's going to be very hard for the sun to boil that ice away. And so that's one of the interesting things there. There's another spacecraft, that would be the European spacecraft called Bepi Colombo, and that will enter the orbit of Mercury itself in 2025. So that's only a couple years away. And so we're looking forward to having more discoveries about Mercury coming up here. So any questions about Mercury before we move on? All right, so this is Venus. This is more or less a visible light image. And so even in this image, I believe it is stretched to bring out some contrast in its cloudiness. Again, to the naked eye, it would look practically featureless. And so most images you see of Venus are contrast enhanced just to give it some stuff to look at there. And of course, Venus is the second planet from the sun. We're going to go in order here. And it's got the highest surface temperature. So it's a little farther away from the sun than Mercury, but the reason it has a higher surface temperature is because of the thick atmosphere around Venus. Venus has nearly 100 times more surface pressure from its atmosphere, so there's a whole lot more atmosphere around Venus than the Earth does. And yet, most all of it, I mean it's like well over 90% of it, is carbon dioxide. Of course, on the Earth, we're concerned about the carbon dioxide in our atmosphere, but it really only comes in at 0.04%. That's a very, very small amount of carbon dioxide in our atmosphere. So it's just interesting that Venus and the Earth should be almost twins, because if you think about it, Venus orbits the sun at about 70% the orbital radius that the Earth has around the sun. So yeah, we would expect it to be warmer, but its surface gravity is very similar to the Earth. It's only a little bit smaller in diameter, and its composition is very similar to the Earth. And so most people, I mean astronomers up until the 1960s, thought that Venus might be just like a jungle-like planet, where it might be very humid there, say, and yet when the first spacecraft went past Venus and started using radio to measure its atmosphere, they started to realize, whoa, wait a minute, the surface temperature of Venus is way hotter than we expected. And so even in the 60s, we started to learn that it was very different. And so with a almost completely carbon dioxide atmosphere and a whole lot more atmosphere than the Earth has, it puts, of course, great atmospheric pressure on anybody that would want to visit there, say, on the surface. And so if you manage to open the door on your spacecraft after you landed on Venus, you would immediately be crushed by the surface pressure. You'd immediately be deafened because the constant lightning would cause such great amounts of sound from lightning, thunder actually, that it would deafen you immediately if you weren't already crushed. And then it would rain on you sulfuric acid. It has rain on its surface, but it's about 900 degrees, twice as hot as your oven gets. And then you'd be rained on by the sulfuric acid. So it's very much, very different, I guess, from the Earth's conditions. So, unlike a twin of the Earth, it's only in its grossest features is it a close twin to the Earth. Otherwise, its surface conditions are extremely different. So I don't recommend going there on vacation. And this here is an interesting image of Venus. This was computer generated via radar. Now radar can go down and see right through the clouds, and it can pick up the surface features of Venus, in essence being able to just look through the clouds. But one of the problems with radar is that it doesn't work like light does. And so the darker features are where the surface of Venus are rougher, and the smoother areas are where it's lighter in color. And so this is kind of a little bit weird in how that works out. But nonetheless, we can kind of see the surface of Venus with radar. And so we've had several spacecraft that have orbited Venus and done radar scans of its surface. And so, again, it was about 90 times the atmosphere that the Earth has. So it's an incredible amount of pressure there.
So is it the clouds that make the temperature higher?
It's actually, I didn't mention it, but it's the greenhouse effect.
Yeah.
You may have heard of that. The carbon dioxide traps the heat, and so some of the visible light does reach the surface after going through the clouds. Not all of it is reflected, but a lot is. And that's what makes Venus the brightest object in our night sky. As a matter of fact, right now, and for the next few weeks, Venus will be visible towards the west after sunset. It'll look like a very bright star-like object. And don't be fooled, many people mistake it for an airplane. Okay? And air traffic control towers have given it permission to land. That's a good thing, too, because if you've ever watched the movie When Worlds Collide, that wouldn't be a good day on the Earth. Anyway, we're not too worried about that happening, though. We know very well where it's going to be. But anyway, again, it will look like an airplane more than a star, if you have never seen it before. So anyway, yeah, go and take a look at it anytime in the next few weeks here in the west after sunset. And so its cloudiness will reflect almost 90% of the light hitting it. That's far more reflective than any of the other planets. So that's another thing that it kind of wins in.
But the craters on Venus like there are on the other
there's only
solid planets,
that's
or is that does the atmosphere help protect it from?
Yeah, no, that's a very good question. There's very few craters on Venus, and they're probably impact craters, but that tells us that the surface of Venus is very young geologically. And so the few craters it does have are probably recent impacts, probably even fewer than the Earth has. And so the most exciting discovery that I want to share with you tonight is that we have detected, and we've pretty much verified, we believe we've verified, that there are active volcanoes on the surface of Venus. So Venus is not a dead planet. It has active volcanoes on it right now. And this actually shows the difference in this hillock here, that it's actually changed shape because of the volcanic action. And so this is actually comparing images from a few years apart and showing that this face of this small mountain is actually bulged in the years between the two images were taken. That's indicating, again, that that's an active volcano. And we've actually also discovered, this image doesn't show it that well, but it does show that there are some differences near the volcano, I should say, and that there are new lava flows. So there are large lava flows on Venus. So that's the exciting thing that I wanted to share tonight. So if we go out another planet out past the Earth, we come to Mars. And I really like this image because if you remember, Mars is only about half the diameter of the Earth. Most people think that it's close to the size of the Earth, even though its surface conditions are the most Earth-like of any other planet. Its surface only would cover maybe a third of the Earth's surface. And so here's the United States compared to the planet Mars itself. And so you can see how much bigger the United States would represent on Mars than it does on the Earth. And this is also known as Valles Marineris, which that is a very large canyon, not crater, sorry about that. And this would way outclass the Grand Canyon. Can you notice how big this is compared to the United States? The Grand Canyon would be right about here in a very little tiny little dirt, or a little gouge in the dirt there. This is absolutely huge compared to the Grand Canyon. It doesn't even really compare. And it's probably because as Mars has aged since its formation, the core probably has shrunk compared to the outer layers of Mars, causing it to stretch in areas. So it's very interesting how its surface has been impacted by the way that the core of Mars has aged. So we're fairly sure that Mars is probably dead or very close to geologically dead. There doesn't seem to be any fresh volcanic activity. But nonetheless, it is the most Earth-like conditions on its surface. And so we also have these images here. These are images taken with the new telescope, the Webb Space Telescope. So you might remember, it's about a year and a half ago now, it was launched out into one of the Lagrange points about 1 million miles from the Earth. And so it's been revolutionizing astronomy as it's been able to be used to take pictures of things. And one of its interesting features, however, is that it's a primarily infrared instrument. It's not a visible light telescope. So in the infrared, we can see very different things. And essentially what it's looking at is heat emissions, not light. So usually when we look at things, we're looking at light reflecting off the surface. It's visible sunlight that reflects off the surface. Whereas when we look at images with the Webb telescope, we're looking at the emitted light from the object because of the heat that it has. And so Mars here is going to be bright because it does emit heat back into space, and so that's what we're looking at here. And so right there is the subsolar point. That's where the sun would be overhead for an observer on that planet. And this area right there is called the Hellas Basin. The Hellas Basin is a large low area. It's probably a very large basin that was formerly an impact basin from a crater. So you can imagine this would be a very large impact crater on the planet Mars, and it's still, even to this day, it's still a low area on the planet. And it shows up here in the infrared very well here. So above here we have a little more details, a little bit different wavelengths of the infrared. And Syrtis Major, this kind of large triangular area, is one of the most obvious areas that we actually see in visible light as well. And it's a large darker area where it's the soil color is darker than most of the rest of the soil color on Mars. And that's what gives us the ability to see these darkened areas. And so this square here represents this square in the infrared using the Webb telescope. This is a former image taken with, I believe, Hubble or something like that. Let's see, do I see there? Okay, I guess it just says NASA and MOLA data. So that would not be, yep, I don't see, well actually this, no I don't see it there. Oh, down here, STS, that's the space telescope for Hubble. Anyway, so some of that data is from the Hubble. And so here's another new discovery from NASA's InSight probe. We've actually had quite a few probes going to Mars in the last 20-ish years. A lot of rovers and even a helicopter that was landed on Mars a while back. So we now know that Mars is somewhat more geologically active than we previously knew. And it probably still has a liquid core. And so that's something now different. But that core is so far away from the surface of Mars that it probably can't generate any volcanic activity. But having a liquid core means that there's still some things that could happen there that we didn't possibly expect anyway. So again, we had formerly thought that the core had completely frozen out, but now we know that looking at Mars quakes, because one of these landers actually has a seismograph on it, it can actually see or detect Mars quakes. And those Mars quakes are telling us that the interior of Mars is a little more complex than we first expected. And one of the things that I think is really interesting is that on Earth, with earthquakes, we can use seismographs, and we know that when there's an earthquake on one spot on the surface of the Earth, seismographs on the other side of the Earth can detect those, and then they can actually figure out the difference in the distances between the different seismographs. We can actually essentially use those earthquakes to probe the interior of the Earth. And so we know very much about the interior of the Earth. You might not think so, but we actually can by using these seismographs. And that's essentially what we're doing here with Mars as well. So very interesting. So if we go out to the gas giant planets, I should say, and we come to the biggest planet in the solar system, and that, of course, is Jupiter. And this is an image taken with the Webb telescope. And we can see that it's very different looking. You probably remember images of Jupiter. I've got some here that we'll show in a minute. But you probably didn't see that the Great Red Spot is so bright. Well, it turns out that the Webb telescope that's looking at heat, or infrared, that giant red spot in the visible wavelengths is actually putting out a lot of heat into space. That's why it's brighter in color there. And so even though these cloud bands match what we see in the visible, with this image we can see which cloud bands are releasing more heat into space and which ones are releasing less. And so that can help us actually look somewhat into the depths of the different cloud layers on Jupiter. Okay? And we can see the rings of Jupiter here. Now we typically can't see the rings around Jupiter from the Earth, but with the infrared capabilities of the Webb telescope we can. So that's why we're able here to see these rings so well, even looking at it straight on. The best view that we've ever had of the rings was from this Voyager spacecraft when they passed by Jupiter way back in the late 70s. They could look back at Jupiter towards the sun, and the rings would actually cause some of that light to be forward scattered, and we could see them much better from behind Jupiter than we can from the front. But the incredible power of the Webb telescope allows us to see these rings straight on. So that's very impressive to an astronomer. And this is a very small moon of Jupiter that's very close, called Amalthea. You can also see that these are areas of essentially auroras at the two poles of Jupiter. Jupiter is interesting in one way also because it's got very little tilt to it. So Earth, as you might remember, is 23.5 degrees tilted compared to its orbital plane around the sun. So it orbits the sun kind of at a tilt, and that tilt then generates our seasons. So during the time when our North Pole is aimed more towards the sun, we're in that area of the orbit where we aim more towards the sun, that gives us our longer days and the higher temperatures in the summer. But only in the northern hemisphere. In the southern hemisphere, maybe you already know this, they have the opposite seasons that we do in the northern hemisphere. So it's not because we're changing our distance to the sun during the year. That's completely false. Because if that were true, both north and south hemispheres would experience the same seasons at the same time, right? So there's very little tilt to Jupiter, but Saturn, the next one out that we'll talk about in a few minutes, Saturn is greatly tilted. It's about 29 degrees tilted. And so it has a lot of tilt, but that also enables us to see the rings tilted towards us at sometimes during its orbit. And so we can see the very beautiful rings. If it was like Jupiter here, we wouldn't see much of the rings open up at all. So that was kind of a lucky break, I guess, for us. So, talking a little more about Jupiter here, we now have Jupiter holding, and this was as of a few weeks ago, that's how quickly the stuff is changing, but assuming it hasn't changed in the last few weeks, it has 92 moons. And so we kind of quit labeling them. And we have to just use Fred and Barney, I guess, coming up here. But most of these being very, very small bodies. We're talking just a few miles across. So at what point do you kind of stop counting these very small icy bodies orbiting a giant planet? I don't know, but somebody's keeping track of it. This image is very interesting because this is the earliest image we have of Jupiter. That's from 1879. That was a long time ago, but look how big the dark red spot was. Of course, this is black and white photography, but that red spot was way bigger back then. And the distribution of the light and dark bands on Jupiter were very different. This has got one really major equatorial band, whereas more modern views of Jupiter, it shows that the bands are much more complicated and not just in the middle there. So anyway, I like to throw that one in because it shows us how much Jupiter has changed over time. And so here are some other images. This is a visible light image, but then here's an ultraviolet light, and this, of course, is in infrared, which is this is a longer wave infrared image than this one. So the Webb telescope, it can use quite a variety of wavelengths of infrared. Did you have a question?
To back up to the aurora.
Why, I can't believe I'm asking this. Why does it have an aurora but Mars doesn't?
Mars has a very weak, almost indeterminate magnetic field. That's the number one reasons why the auroras happen at the poles of a planet. Now, you might even know this, the magnetic field of the Earth is not perfectly aligned with its rotational axis. It's somewhere in northeast Canada, I think, is the north magnetic pole. But it's close enough, and it keeps the charged particles from the sun and the solar wind to kind of spiral down towards the poles, the magnetic poles of whatever planet we're talking about. And so that's what's going on here with Jupiter as well. So that's why we have major auroras much bigger than the Earth has. But that's a very good question. And we could keep talking about that kind of stuff, but I do have to move on, I guess. So these are just very interesting. But did you know that there's currently an active spacecraft in orbit around Jupiter right now? And that spacecraft is called the Juno spacecraft. And it's very interesting because Juno, being a very cheap spacecraft, I mean, in relative terms, it's not cheap, but nonetheless, to keep this spacecraft from breaking the budget, it's actually rotating pretty quickly to maintain its stability, which makes it really hard to take images with, but we are still able to take pretty amazing images here with Juno. But it's very close to the surface, and so it's a geographic or geometric distortion where it's so close to the planet that it makes it look like we're looking at a very small area of the planet blown way up. And so that's why this image looks very distorted. But here you can see the great red spot. And this is one of the other oval storms on Jupiter that's kind of right over. And so the great red spot, though, it was able to image it from such a low angle that we could actually tell that it goes very deep into the atmosphere underneath it. So even though it's kind of a surface storm, it has a much deeper root to it than we expected. And it's probably churning up material. Its chemistry is going to be a little different in deeper layers. And it's churning up material from a much deeper layer, and that's what probably gives it that very strong reddish color. So that's probably why. See, these white storms, they're not able to churn material up from a very low level in Jupiter's atmosphere. And one thing to remember about Jupiter is it's almost all gas. It's not like a planet that's just got an atmosphere around it like we think of on the Earth. Instead, it's got probably about an Earth-sized core at the center. If we go back here, the great red spot is about 1.5 or so times the size of the Earth. So that's all the size of the solid core is probably way, way deep in the center of the planet. The rest of it is all gases. So you can just think of it again as a gas giant planet. That's where they got that name for it. And so the depth of the great red spot is on the order of, we believe, 200 miles, which is pretty deep. And so if we think of a hurricane on the Earth, which is kind of similar to what the great red spot is on Jupiter, but 200 miles thick, that's way thicker than the Earth's atmosphere is. So anyway, that's a very interesting new discovery about Jupiter and its great red spot. So has anyone heard any of these discoveries so far? The newest discoveries? So I'm hoping that they're interesting enough, though. They're not just too obtuse to be interesting. So let's look at Saturn here for a moment. And Saturn, again, has these very, very beautiful ring system. It's likely that this is a moon that got so close to Saturn that it broke up due to tidal forces. So Most of you probably know about the tides on the earth. That's from the same root word, tidal actions. It's the same root word because the moon causes the earth's oceans, because they're not solid, to actually rise up and move towards the moon a little bit. And what's really freaky is that if you look at the moon in 3 dimensions, or the earth, I should say, sorry about that, I'm thinking about the moon, but the earth in 3 dimensions, it has a slight bulge in its oceans going towards the moon, okay? And that shouldn't be too surprising if you think about it. But on the exact opposite side of the earth, there's also a bulge where the oceans actually kind of get a little bit piled up compared to the center of the earth. And actually what that means is that the moon is pulling on the near side of the earth stronger than it's pulling on the middle of the earth. But that's even a little stronger than the far side of the earth, which means it leaves behind that ocean on the opposite side of the earth compared to the moon, and leaves kind of a bulge of ocean on the other side. And that's one thing that when I first learned that, I was kind of blown away, really. So it's actually the earth is being pulled closer to the moon more so than the oceans on the far side of the earth, leaving behind a bulge there. So anyway, so that tidal stuff that we're talking about, when something gets too close and orbits too close to a very large body, those differences between how hard it's pulling on the far side versus the near side of that body, it can get so strong that it can actually rip that body apart. And so that's probably what happened to a moon of Saturn to form such a wonderful ring system. Because this is not solid at all. This is trillions and trillions of particles, boulders of ice, essentially. And water ice is very reflective, and so that's why it's so bright. And from a distance, it looks solid, but if you got way up close, you'd notice that it's not solid at all. Okay, and there's a gap here. This was noticed by the astronomer Cassini. He was a French astronomer back in, I believe, the 1780s. And there's another smaller gap here, and that was named after the astronomer that discovered that one. That was Encke, the Encke division. And if you could see that there's a little bit of a very faint ring inside. You probably can see it right there, the best against the planet. But that is known as the crepe ring because it's a very thin ring. But nonetheless, because of the tilt of the planet, that's how we can see those rings opened up like that. So if we traded the rings for Jupiter with Saturn, we wouldn't have nearly the beautiful planet that we have with Saturn here. So let's move on here. So this should look different. This is taken again with the Webb Space Telescope. And notice how now the planet is very bright, but the rings are very dim. They're actually very cold. If you think about it, this should make sense. With the rings being made of ice, a very reflective surface, they also very efficiently get rid of any extra heat. It can emit that into space very effectively. And so it leaves the ring particles very cold. And that's why they're nearly invisible here. And yet we have this very bright ring here on Saturn. That's where it's emitting a lot of its heat out into space. And then notice at the pole here, it's very bright. So there's a lot of heat coming out of the North Pole there. So this is a very, very interesting planet in different colors. And I want you to notice this here. Notice its shape. Can you tell what kind of shape that is? It's known as the hexagon of Saturn. It's only visible on the North Pole. The South Pole does not exhibit this. So only on the North Pole. And there have been experiments that show if you have a rotating system like this, that a stable hexagon can form. And so apparently that's what this is. It's not ancient aliens. Okay, sorry to break your bubble there. But a stable hexagon can form in these conditions. But it's very interesting, isn't it? So here's a natural light image of it. Now it's not animated, of course, but there it is. So yeah, when astronomers first discovered this on Saturn, they were very shocked as to what's going on there. It's very weird. So anyway, that's another very interesting discovery. So let's go to Uranus now. And so this is a very bland-looking planet in the visible wavelengths. It definitely does have a bluish-green color to it. But beyond that, at least in visible wavelengths, without stretching the contrast really high, there's very little things to be able to be seen there. But this is an image from the Hubble Space Telescope, and it shows a lot more detail than we can see with Earth-based telescopes. But on the right here, we see the planet and its rings much better with the Webb-based telescope. This would be infrared. So the rings are shining very brightly in the infrared. It's very interesting that that's opposite of Saturn's rings. But the color of the rings and their composition is actually different as well. Uranus's rings are very dark, practically coal black. And so they are very inefficient at radiating away their heat. And so they're still warm. And so in the infrared, we can see them actually very well. It almost seems a little bit ironic in how that works, but you can also tell that Uranus has a tilt of its axis of over 90 degrees. So it's kind of rolling on its side as it orbits the sun. That's one of the very strange, weird things about Uranus. And so here is another image, and some of this, the pinkish color, is from X-ray radiation. So we have a telescope above the Earth's atmosphere that can detect X-ray radiation. And so we've combined this with visible light images from the Hubble telescope, but we can see this, of course, very interesting pinkish color, and that hasn't been detected on many of the other planets. So it's not unknown, but it's just a new discovery that most people probably aren't aware of. And this was taken when Uranus was in a different spot in its orbit, and we can see that it's not quite as rotated around in its orbit as it was later when we saw the picture taken by the Webb Space Telescope. But anyway, let's look at Neptune. Neptune and Uranus are very close twins, although Neptune is about half again as far out. So Neptune is very far out, and it's the farthest of all the planets. So it's very similar again to Uranus, but notice the color is much more blue than green. But both the blue and the green colors are probably due to methane. Methane gas in the atmospheres of these two planets is what gives the reflected color this very interesting blue or green color. And the arrow is pointing to a resurgence of an object known as the dark spot, the great dark spot, sometimes it's called. And nearby it has actually probably water ice clouds. That's what the white clouds are. And so there's something disturbing the very upper layers of the atmosphere of Neptune and causing these probably water ice clouds to form very high in its atmosphere. So this is a much better picture of that great dark spot, so as opposed to the great red spot for Jupiter. And notice we've got a couple of very nice stripes down here, and that's another dark spot orbiting down there. But one of the things I wanted to point out to you is this body right here. That is the large moon of Neptune known as Triton. And Triton is a body that is very similar to Pluto, the dwarf planet. And so notice if you look at it for a while, is there a fruit that this kind of reminds you of? Cantaloupe, that's exactly right. So people actually refer to this as the cantaloupe terrain on this moon Triton. And Pluto also shows that. So I've got a couple of slides here a little bit later that will show you the same thing. But this moon is at the very edge of our solar system for the regular planets anyway. And so the temperatures out here are extremely cold. And so we didn't really expect to see a lot of interesting geology out here. We mostly expected to see a bunch of craters, and that's about it. But look, there's very few craters in this image, aren't there? So what's causing the heat to process the geography here? I mean, it's very interesting to look at and the different areas. Now, this is very interesting here. This streak here seems to be starting from this spot and being blown in the direction towards the upper right. And that does seem to be exactly what's going on here. There seems to be prevailing wind direction in its very thin atmosphere that's causing the output of whatever this is probably like a geyser, and the material is landing on the surface downstream essentially, and it's darker material. So that should help us to try to figure out what this material is. But this is at like minus 350 degrees Fahrenheit. I mean, what is this that's going to be active at such a cold temperature? So, very interesting. And what about these rills? I mean, there's got to be something that's making those, but it's very difficult to figure out at these temperatures what that is. So, of course, we've looked at Neptune with the Webb-based telescope. And so here we can see the rings are actually relatively bright in the infrared, and it's pointing out to several of its other very small, newly discovered moons. And so up until about 15, 20 years ago, we only knew of 2 moons, Triton, the very large moon, and Nereid, which Nereid orbits very far away from Neptune. So, let me see if there's anything else I was going to say about that. Okay, that is going to the next slide. So, yeah, this is a visible light image, but this was taken with the Hubble, I believe. Yep. And then there's an infrared image. This was taken with the Subaru ground-based telescope. Of course, the Japanese would name it Subaru. Actually, Subaru is the name of a very well-known star cluster in the sky. Do any of you know what that star cluster is called in at least English-speaking countries? It's known as the Seven Sisters, or the Pleiades. That's very easy, naked eye cluster of stars you can see, and the Japanese call it Subaru. And the car company Subaru started because they had a conglomeration of 6 smaller companies that started Subaru to make cars, and they decided to use the name Subaru because it represents 6 easy-to-spot stars in the star cluster. So anyway, more stuff than you probably wanted to know. So anyway, this again is the James Webb telescope, and this is as well a little bit different. And that's the Voyager 2 spacecraft. That was back in 1989 when it took that image. And here is Pluto. So even though it isn't an official planet, I decided to include it because it's so cool looking. Now this is from the New Horizons spacecraft that passed Pluto back in 2015. And this has been contrast enhanced, so unfortunately it doesn't quite look this good to your unaided eye, but nonetheless, when it was lower or farther out, when we couldn't see as good a detail, this image here, it kind of made it look like it was half a heart, and this kind of very faintly looks like the other side of the heart. So this heart-shaped region there is very identifiable to Pluto. But then look at this area. That is like majorly red colored. Even in the visible light, non-stretched images, it's still very much a pink color. And then here's some blues. I mean, again, we expected to pass by Pluto and look at this really old-looking chunk of ice that's been battered by asteroids and comets, and that's about it. But no, just like with Triton, there's obviously some kind of geology going on here, isn't there? So very cool geology that we're discovering. We also have kind of figured out very recently that Pluto is in kind of an in-between area in its orbit around the sun. It turns out that Pluto's orbit around the sun is very egg-shaped, and what astronomers would call that is eccentric. So it gets very far away from the sun at one point in its orbit and then relatively close to it in another part. And when it's closest to the sun, it's actually closer than Neptune is. But the tilt of the orbit of Pluto is such that they could never collide. Okay, so they're not going to ever collide, but nonetheless, it does get closer to the Earth and the sun than Neptune is at times. And so again, this in some ways is very similar to Triton. And so here's a very interesting things. These blue areas are what we're actually trying to highlight right now. And those are likely to be where new ice buildups have occurred relatively recently. New ice does behave a little differently than old ice. it turns out that cosmic radiation will make it be a little bit darker. And so these areas are where we know that this ice has been very recently either deposited or exposed to fresh sunlight. And so those are geographic areas that, hey, something's going on there. We're not sure exactly what yet, but things do occur even at these extremely low temperatures. And so we're still trying to, of course, figure out what is going on here. We thought that these temperatures of almost minus 400 degrees would be completely dead, but that's not the case. So how about if we just look back at the Earth? We're, of course, making all kinds of discoveries about the Earth. We live here, but let me just mention a little bit about it. So this is, of course, our home planet, the third from the sun. But the new discoveries about Earth are happening all the time. And, of course, understanding our own planet will help us understand what other planets would need to be able to support life as well. Of course, most people are very interested in other planets that can support life. So it's very instructive to us to look at the Earth and understand what makes it so habitable compared to the other planets. And it turns out it's not just the presence of liquid water. Although that's a necessary condition, that's not a sufficient condition to enable a planet to support life. It turns out there's a lot more of them than we ever dreamed. So one of these newly discovered parameters that allows life to exist on our planet is the gas in our atmosphere. So the most abundant gas, though, that most people don't talk about very often anyway, is nitrogen. Okay, we talk about the oxygen, of course, is very important to life, and we talk about carbon dioxide, even though that's a very tiny fraction of what makes the Earth's atmosphere. But it turns out that nitrogen, it's on about 70% of the gas in our atmosphere that we're breathing right now. It turns out it's much more important that we have this nitrogen in our atmosphere than we at least originally thought. And so there's an article from space.com. It says we don't understand exoplanet habitable zones as well as we thought we did just a few years ago. So that was my last slide, and I wanted to make sure that I didn't have a whole bunch of slides I didn't get to show because I usually talk so much. But anyway, so we can certainly entertain some questions here.
You mentioned geological activity. Not quite sure how to ask this, but is that just kind of something of interest, or is it a thing that's necessary to support life, or is it necessary to have atmospheric changes, or what? Is there some sort of implication of geological activity beyond just, hey, that's neat?
Yeah, that's a very good question. Only with the Earth are we right now thinking that it could have something to do with habitability. But nonetheless, the thing that's surprising us is that at these very cold temperatures, I mean, we're talking way colder than your freezer at home. So at those very cold temperatures, how is it that this, probably mostly ice and other things that we, it's just interesting because you can't talk about ice at those temperatures like we talk about ice on the Earth, because the ice at those temperatures is harder than granite. So it's very hard. So how is this very super cold, hard ice moving around and doing things? That's what we're trying to understand. I'm not saying here that we understand it, but it is, something's going on there, and it's very interesting. It's a lot more interesting than we thought it was going to be, which is always exciting. Yeah, when we talk about the Earth, there's, of course, many different parameters. I've seen that not just are we talking about a habitability zone, which usually refers to the temperature at which water can exist in all three phases on the surface of that planet. That's just one of about 14 habitable zones. Some of those include, say, the amount of ultraviolet light coming from its host star. And it turns out that photosynthesis is very interesting in that it only can work, as far as we understand it so far, with visible light. Visible light happens to be at the very sweet spot where there's enough energy in each of those photons to cause the chemical change that's needed to make sugars from sunlight. Because if you have a more energetic star and you're within the habitability zone for water, you might get then with a brighter star too much ultraviolet light. Well, that's going to break down the very delicate molecules that enable photosynthesis. And then if you have around a star that is cooler than our star, the sun, it's not going to have enough energy in those photons to trigger a chemical change to, again, make life possible. So it seems like there's a bunch of interlocking things. And so that's one of the things that is becoming more and more apparent, I guess, with discoveries on the Earth. Because we're very curious, well, you know, is it that life is throughout the universe? Well, it kind of seems like that is pointing more away from that at this point, just because we are understanding more about how the Earth is so special to enable life to exist on its surface. Anyway, hopefully that somewhat answered the question. Yes?
So can you explain the distinction again between a dwarf planet, a planet, and an exoplanet?
Okay. An exoplanet is beyond our solar system. So within our solar system, we have planets, and then a planet has to sweep out its area around the sun where that planet is. So that usually means that that planet has to be in a very circular orbit. So Pluto actually flunks that test. It's so egg-shaped, it's not very circular. And let's see, what are the other two conditions? I'm just blanking here. But it definitely flunks that condition. And so, if you might have noticed, I mentioned minor planets because that's how they kind of kept the asteroids from becoming planets. And so dwarf planets don't sweep out gravitationally the zone around them in their orbit. And gosh, what was the other ones? I'm sorry, I'm blanking right now, but there's 3 conditions it needs to satisfy. And I know that that one is one that Pluto doesn't match. Any other questions?
Moons of Jupiter, any news, any new news about the various moons of Jupiter? You hear various, or over years I've heard various things about Io and Ganymede and
Sure.
ice volcanoes or something.
Yeah, no, we could have spent quite a bit of time on Io.
News.
Io is,
Summarize in a minute.
yeah, Io is the most geologically active body in the whole solar system. They're saying that Io's surface is basically recoated with the ejecta from volcanoes about every decade or so. I mean, it completely refreshes everything on its surface to such a depth, and that's how active the volcanoes there. And one of the things about Io is that when you get to the outer solar system, objects just necessarily have a lot more water as part of their composition. So within the inner solar system, essentially within the asteroid belt, the area around the early sun was so warm that it drove off water. It would turn it to steam and it would be pushed away from the inner solar system. And so we have kind of a residual water that was both from some of the materials that the Earth was made of, but also probably replenished with cometary impacts. And so, but beyond the asteroid belt, suddenly we have, say, Jupiter, and its major moons are mostly made of water ice because there could be water there. It's beyond what sometimes is called the frost line of this early solar system. So anyway, but Io has practically no water because it's so volcanically active that the water ice has just been driven away. It's essentially melting point is so low that it gets sent into space via the volcanic activity, and then it recollects in other places, even in Jupiter itself. And so Europa is the second moon out, and so it's a lot more water ice. There's still rock and other materials, but there's a lot of water ice with Europa. And Europa also suffers not nearly as much as Io does from the process that heats Io and makes it so geologically active. And that is when Io is orbiting around Jupiter, there's 3 other large moons of Jupiter beyond Io. And so when it passes between Jupiter and one of those large moons, it stretches it quite a bit, and then it relaxes. But every time it passes between Jupiter and one of the other large moons, it's stretched out. And so it's just constantly being worked on, and that's the energy that goes into it that comes out as volcanic activity. Europa also suffers from that, but not nearly as much. But because it's also being stretched and stuff, we're estimating that there is a liquid water ocean under the ice of Europa. And so many people have suggested, well, maybe there's life under the ocean or under the ice of Europa's surface. And so, and when you look at pictures of Europa, there's practically no craters on it. All the crater-like things on Io are volcanoes. And then Europa, there's just a handful of craters because the surface is constantly being massaged, and it causes those craters essentially to just erode away. And so, yeah, there's a mission to Europa. I can't remember its launch date, but it's probably another 5 or 10 years out. But we are planning on sending a mission to Europa and trying to at least drill through some of that ice. I don't know if their plan is to be able to reach liquid water or not. I kind of doubt it because the ice
From
is
NASA
pretty
or
thick.
from one of the other agencies?
I think it's the Europeans are the primary ones doing that.
Thanks.
Sure. And we do have the test, so if you're ready. All right, I'm just joking. Yeah.
As far as listening to your talk here, it doesn't sound like there's really a habitable planet within our solar system. Have you heard about anything beyond our solar system that we might want to venture to at some point?
Well, I don't know. It just looks like statistically, habitable planets are probably more rare than we estimated at first. I mean, in the 60s until probably the 90s, it was common to think that, yeah, there must be, maybe even elsewhere in our solar system, but as of right now, it doesn't look like it, but that's one of the reasons we're going to try to go and find out, which is always exciting to know whether there is or isn't. But yeah, in terms of exoplanets, it's just so difficult to examine them because we're just barely able to detect them. And so being able to do much more than that, at least in the near term, is still going to be beyond us. But we are looking at building very large space-based telescopes, somewhat similar to the Webb, that will be able to actually examine them at the limit of our technology and be able to find out more about them. We may be able to, say, figure out the compositions of these atmospheres of these. And so we can usually tell their orbits around their host stars, and then if we could also examine directly their atmosphere, that could be actually proof one way or the other, because the Earth's atmosphere almost certainly wouldn't have oxygen in it if it weren't for life. So right there, that would be a way that we could tell if there's life in other atmospheres anyway. So yeah, you might want to just thank life for the oxygen we have to breathe here. Yeah.
So how many planets or moons have we actually landed a rover on?
Wow, that's a good question. It's probably just Mars right now. We have landed on Titan, which is a moon of Saturn, the largest moon of Saturn. We've landed landers that have only lasted about an hour on Venus because the conditions are so drastic. And of course our moon. But beyond that, not a whole lot. I mean, we have landed on some even comets, but actually rovers, I think that's pretty much only the moon and Mars that I can think of off the top of my head. Interesting question. Yeah.
And then of the telescopes that are now in space, is the Webb the strongest or
Oh, yeah.
detects the farthest?
Yeah, it's the
And are those real-time images that the operators are seeing?
Typically not. What they want to do is take time exposures, and so a lot of these images of very dim things can be on the order of many minutes to hours. And even sometimes when they're really trying to look at the very dimmest things, they can actually take exposures that are literally weeks long. So yeah, it's a variety. The planets, that's just a fraction of a second, and the detector is going to have a full image, but a lot of the dimmer objects, they need minutes, on the order of minutes.
How far out is the Webb telescope?
It's about 1 million miles from the Earth, but it's kind of in an orbit around the Earth. Between the moon and the Earth, there's certain positions where there's relative islands of stability, so to speak, And that's where it is. It's in what's called L2, or Lagrange point 2. And so it's beyond the Earth compared to the sun, about 1 million miles. But because of the moon and its orbit around the Earth, it keeps that spot relatively stable. And so it only needs to use a small amount of minor or small rockets to keep it in that spot. And they chose that for several different reasons, one of which is that it will never look directly at the sun, and that's the direction the Earth is too. So it keeps the Earth out of the way, essentially, by doing that. Yeah, great question. All right, well,
So will you be giving this talk again? at
not
some
that
point?
I know of, but yeah, I just love talking about this stuff, so if they invite me back,
Well,
I'll do
thank
it
you.
again. You're welcome.
Yeah.